Good afternoon to everyone. So, actually, my topic isn't directly related to forest inventory, but we just made a little change between the Yevgeny, who cannot make it today, so he will present his presentation tomorrow. So, what my presentation will take care is that at first I will show you one example how to measure or estimate the volume of the wood chip trucks in a different way than a laser scanner. And after that, of course, I will describe some image processing texture analysis cases which we selected here, so how to evaluate how homogeneity the biomass is and how to estimate the chip size. So, at first, this volume estimation part. So this study was made partly in the Tekes-funded BEST project, Sustainable Bioenergy Solutions for Tomorrow, and it will end of this year. And the main focus of this study, or my part, was to evaluate, do we have any low-cost methods to measure the volume of the wood chip trucks. So we tested two different approaches. First, based this structural light approach. So for example, this sensor is used in gaming industry, Kinect, I don't know, have you heard it? So we can measure the 3D shape by analyzing the projected speckle pattern and recreate the 3D model. And it's the second part, photogrammetry. The 3D model is made by analyzing separate images which are taken from separate different places and different angles, so we can form the actual 3D model. And this is used in remote sensing applications. Like, we also tested that method in this project in Varkaus pulp mill. So we use drone. Do we have the laser? So we use drone here. We try a couple of times over the wood chip piles, and after that we extract every 13th image from the video and use that to create the final 3D model. And this is the actual part. So we make this kind of experiment at the Joutseno pulp mill. So we try to measure the volume of the chips inside the truck. And there were very nice place where we could make our experiments. There was very large hangar where we could install our cameras, and there is also Kinect sensor, but I don't show those results here in this presentation. So our truck was filled with different payloads, and it was driven under our camera, and we can detect the surface of the pulp chips. So there is one example measurement, actual measurement.
Saa mennä.
Oho, sounds. So this is measured just by using normal digital camera and the full HD resolution. And by using that video, we can reconstruct 3D model from that container. And how to calculate the volume actually from this container is the next part. So this every analysis was done by MATLAB, and the models didn't they were not scaled in the real world coordinates. Of course, it is possible to do it. We just need to know some dimension of the container, so we can scale the model. But we used only relative scaling. And this is one interesting example. We didn't use any edge detection functions here to our point cloud. So we just converted our container to single cube, and we can extract the borders out of our data. And we can get the height of the borders, and we can compare that to what they are inside of the container. And there is some experimental payloads. We used 4 different cases, and of course there is some missing parts because the camera didn't see the whole area of the container, but still it doesn't matter so much because we can estimate the fill-in rate by using all the rest of the material which is included in our model. The next part is this texture analysis. So this part is done by Aki Nissinen, who is doing his master thesis about this. And the goal was what methods we can use to detect some useful quality parameters from our data. So, for example, how homogeneous the biomass is. Is there any rocks or something else what doesn't fit to our data? So he used this detox method, which is previously used, for example, breast cancer analysis, and is used for paper roughness analysis. So it is used for separating highly varying textures from the smoother ones. If there's lots of variation, we can detect some bigger objects very easily from our scheme. There's some example of our roughness maps. So we can see that there is this very large particles which are easily seen from our roughness map. If there is lighter areas, it says that there is lots of variation. But if there is darker places, the surface variation is very low. And this question, how to estimate the chip size? This is a very hard question, actually. There's plenty of studies which are trying to solve this. Of course, we would like to solve that also. So there is problems with the overlapping particles. They're very hard to detect or discriminate to each other. So how to improve our solution? So we tried many single approaches, but neither one of those didn't work so well. So we need to combine different methods to get better results. So here's that example image. We have done some medium filtering and Gaussian filtering for that. So medium filtering will try to preserve all the edges. And this thresholded mask is calculated by Otsu method, and there is some morphological operations also involved. So we make a mask, and use that to our filter image, so we can separate some particles from our original image, and we can get this lots of measure this. Some parts of the unwanted features are removed. And after that, we used this masked image here to calculate the edges of that. And the left part, that there is these edges, they are filled. And this is the normal case where in many cases the overlapping parts are classified as a single chip. It's not wanted result. Therefore, we make the extraction of the edges from that image and make some morphological operations so we can make the separation more clearly. And from this image, we can make the labeling, and we can actually make we can identify each chips and make some kind of estimate what's the chip size of our image. There is some example images what we have also measured. This works pretty well compared to previous studies which I have seen. And the chip size distribution follows pretty much. And actually, these images are scaled by using the ruler. First, we take the images by using the ruler, so we can get the actual metric for our analysis. Conclusion. So, in this study, we use the photogrammetry, and we try to solve, is it possible to use that image analysis methods to estimate the volume of the trucks? And it worked pretty well, and actually it's relatively fast. And of course the model resolution can be increased by using higher resolution camera, of course. And these models can be imaged from moving targets by using one camera, or from stationary position. For example, when the truck comes to the factory, it will be scaled. Then we can take the several images from different angles and take the necessary information. And this chip size estimation, it can be adjusted and calibrated more accurate by using some reference methods, so some chip classifier like for example, Technosavo's 3D chip smart machine. Thank you.
Thank you, Jukka. This was most interesting. It's fascinating to see how you can use different technologies in completely new way. For example, you mentioned the Kinect, the gaming device. You can combine it with industrial production. That's a very, very fascinating idea. Any questions?
Are you doing any work with moisture analysis of the chips?
Yes, of course, but not in this part of the project. In this huge BEST project, there is one part which take care of the moisture problems. Try to solve that. It's the tricky one. Yes, yes.
We will handle that in next year's conference, so please welcome. Perhaps it's still unanswered question at the moment.
Yeah.
Any more easier questions over there?
What requirements do you have for the camera, specification-wise? How good does that be to be able to use this analysis?
Basically, I have make some experiments with my mobile phone camera. It's not so you can use very low-end cameras also.
The mobile cameras nowadays, these are excellent. These are excellent resolutions. Resolution might be the key, however, if you want to make precise measurements, you need high megapixel count.
Yes.
But otherwise, I don't think the other specs of the camera are not so important, like signal to noise frequency,
Yes, no.
etc. Over there.
What is a rough distance measurement accuracy of Kinect in your
Distant measurement accuracy. Actually, it was, if I remember correctly, the accuracy for determining, for example, table size, it was few millimeters. But I don't remember what was the actual distance from the, what was that accuracy? I think it's very quite accurate. This was the first generation Kinect, this one. I think the generation 2 is more accurate and it will give you better results.
Kinect must be very accurate, otherwise it wouldn't be useful for gaming, because those gamers, they are so demanding. They have high requirements for techniques. If it's good for gaming, then it's good for production use also.
Yes, of course.
Yeah. Okay, over there.
How precise is the volume estimation solution compared to the actual measurement? I mean, I understand that you are seeing homogeneous volume. What if there are volumes inside? I mean,
Of course, we cannot consider those if there is some hollow points or something like that. So that's only estimate from the surface shape. So
in that case, considering that there are no volumes, your measurement is how close is to the actual measurement that's coming out traditionally?
actually, it's very hard to say because normally at the moment they don't use these laser scanners or anything other reference devices in the pulp mills, or at least in Joutseno, and they are using only measuring stick. Of course, I can say how accurate is against the measuring stick, but that's not so good result. So it's very, I cannot say the exact result, but I think the models are pretty precise and they produce good